So, what I plan to do in these lectures is to discuss some aspects of string perturbation theory. Okay. Now, I am certainly not going to describe all aspects of string perturbation theory, okay, but we will focus on some particular aspect. So, let me begin by saying what aspect of string perturbation theory that we will be discussing, and this has to do with mass renormalization. Okay, and as we go along, we will see why this is important and interesting. So, the plan is that first I will try to introduce what the problem is. Okay, this in fact is not generally discussed. So, first, what is the problem with mass renormalization in string perturbation theory? Okay. So, then in the second part, okay, which will be the main part of this these lectures, we will discuss the solution, and this will be based on some recent work that I did with Roji and Arnav Kundu, who is in Cambridge. Sorry, Arnav Rudra, who is in Cambridge. And then in the third part, we will try to go beyond what we discussed, so other applications, other possible applications. So, let me begin by describing briefly some aspects of string perturbation theory that will be relevant for us. So, first of all, I think you are hopefully all familiar with the fact that the string theory or the string perturbation theory is based on what is called the first quantized formulation. So, you do not have any Feynman diagrams. Instead, what we have is Polyakov prescription. But is this visible from everywhere? What I am writing? Okay, but with that screen and everything else, it's visible. Okay. Okay. So, Polyakov prescription. So, this is a prescription for computing n-point amplitude in string perturbation theory, okay. And the prescription goes like this. So, the n-point amplitude is given by, first of all, is sum over genus. Okay, so this G counts the number of loops. Okay. It involves an integral, okay, over what I am going to describe shortly. So, let me write down the full expression and then I will try to explain the various parts of this formula. Times some dots which I will describe later. So, let me try to explain briefly various parts of this formula. So, let me start with this. Okay, so, sigma Gn, what does it mean? This is a genus G Riemann surface, okay, a genus G Riemann surface, which is a Riemann surface with G handles. With n punctures. Now, these punctures is a technical word that people use, okay. But essentially punctures on a Riemann surface mean that there are n marked points on the Riemann surface, okay, n particular points on the Riemann surface, and those are essentially the points where you are going to insert the vertex operators. Okay. So, in this expression, the zi's are the locations of the punctures. So, what are these? So, these are what are called vertex operators. Vertex operators. So, for each external state, so we are called computing the n-point amplitude. So, for each of the n external states, we introduce a vertex operator, okay. And these vertex operators are BRST invariant and conformal invariant. Invariant operator in 2D CFT, in some 2D CFT, which describes the particular string theory that we are interested in. These ones, these dots are some insertions involving the ghost fields, which come in quantizing string theory. And finally, this integral MGN, this is the moduli space of genus G Riemann surface with n punctures. So, roughly what you do is that you take for a given amplitude. So, an amplitude is of course characterized by what external states you have. So, n external states. So, for each of these external states you have a vortex operator. You take the product of those vortex operators, calculate the correlation function, okay, together with some additional ghost fields which are universal, which does not depend on the external states that we have. Okay. So, you calculate this correlation function on a genus G Riemann surface with n punctures, and then you integrate this correlation function over the full set of genus G Riemann surfaces with n punctures. Okay. So, MGN, the moduli space, essentially means that it is the space of all possible inequivalent genus G Riemann surfaces with n punctures. So, this gives you an amplitude at G loop order, and then of course to calculate the full amplitude you have to sum over G. And you will recognize that this way of writing an n-point amplitude is very different from Feynman diagrams that we use in normal quantum field theory. In particular, at G loop we have only one term instead of sum over many Feynman diagrams. We have one term. And usually this is stated as an advantage in theory, that in string theory you do not really have to sum over many diagrams, you have just one term. But as we will see, advantage will turn into a disadvantage when you are dealing with this problem of mass renormalization, okay, which I have not even introduced so far. Okay, but this is just some aspect of perturbation theory that I want to emphasize. So, what does this amplitude calculate? Okay, what does AN compute? So, let me say what it is supposed to compute. So, AN is supposed to compute a matrix element. Okay, by n point S matrix element I essentially mean an S matrix element with n external states. So, first let us ask, does it really do what it is supposed to do? Okay, does it really compute the n point S matrix element as we are normally told AN is supposed to do? So, to see whether it really computes the S matrix element, let us go back to quantum field theory for a moment. Okay, so, forget about string theory and just remind ourselves of an expression for the S matrix element in quantum field theory. So, S matrix element in a QFT. And this is given by what is known as the LSD prescription. So, let me write down the expression for the S matrix in a quantum field theory according to LSD. So, I will call that Sn, okay, to distinguish this from N, because you want to eventually compare whether this S matrix element is really the Polyakov amplitude. So, here is the expression limit of Ki square going to minus m Ai p square. Okay, again, I will try to explain the various parts of the formula later. Ai p, Ai comma p. Okay, I will explain what this p stands for. Okay, so let us start with this. Okay, this is the endpoint Green's function. Endpoint momentum space Green's function. So here the convention is that A1 to An, okay, are the quantum numbers of external states. K1 to Kn are the momenta. This one MAIP, this is the physical mass of the ith particle of ith particle. Okay. And when I say physical mass, this is the physical renormalized mass, okay, the quantum corrected physical mass of the ith particle. That is what you have to put here in this limit. And this Z is what is called the wave function renormalization factor. So these data, the Z and MAIP, these are in fact given in turn by the 2-point function, which I am going to write down next. So these are computable in a quantum field theory, okay, MAIP as well as ZAI.
I can compute the 4.2 level without the external expression.
Yes, you can. You can. Yes.
So then I don't need to. So G here you are saying not amputated diagram.
No, G is a full Green's function in quantum field. Yes, you could compute amputated diagram, which will correspond to removing. Well, you will not move everything. Okay, there is still a factor of Z left over. Okay, so that you have to put in. Okay, but this is the original LSD prescription for in terms of Green's function. Okay. Now, how to define these objects? Okay, so these objects are defined in terms of the 2-point Green's function. So G2, A1, A2, K1, K2. So this is given by, first of all, there is a momentum conserving delta function 2 pi to the d delta d K1 plus K2, and then there is a delta function from the quantum numbers. Okay. Now, this is a simplification that I have here, and in fact, in general in string, a more complicated matrix. Okay, but let's just write it as a delta function delta a1 a2, so that the 2-point function is non-zero only if a1 is equal to a2. And then the non-trivial part is z a1 of k1 over k1 square plus m a1 p whole square. Okay, so I should have said this p stands for physical. Okay, and we will see the m without the p in a few minutes. So this defines z and m a1 p. Okay, so this is required to have the property that this has no poles or any kind of singularity at k1 square equal to minus m a1 p square. Okay, so this is a perfectly smooth function. Okay. Often one just gives the whole part of it, so you just think of this as a constant, which is the value of this evaluated at k1 square equal to minus m a1 p square. But we will keep it like that, this for because it just makes some of the expressions simpler. So all the poles of the Green's function comes from the denominator. Okay. So from this viewpoint, okay, after you have factored out this trivial factor, the kinetic part, okay, m a1 p is the location of the pole in the k1 square plane, okay, or minus k1 square. Okay, that gives the that defines m a1 p, and z in the denominator is the residue essentially, okay, near the pole. And those are the values that you have to substitute here to compute the S matrix element. Yes.
So Z, is there some constant on Z? I mean, Z can have say branch cut or anything. Is there something?
Well, yes, higher order Z can have branch cut, but near k1 equal to m a1 p, it shouldn't have anything. Right? At other values of the momentum, see, we are only interested in knowing this, knowing Z near k1 square equal to minus m a1. Right? Because you can see that in this expression, place where you need to evaluate Z is around on the pole, right? And there it shouldn't have any singularity. Okay, it should be perfectly smooth analytic. It should have a Taylor series expansion in parts of k1 square. Okay, so one could ask, is this the analog of what the Polyakov amplitude computes? Right? This is what we really want to compute in a quantum field theory. And does Polyakov amplitude really compute what it is supposed to compute, namely this one? Okay, had you been doing a quantum field theory? Now, the answer unfortunately is no. What Polyakov amplitude computes, okay, if you want to translate this in the language of a quantum field theory, okay, it's slightly different from what you have written there. So, Polyakov amplitude computes the following quantity. Where you have two quantity MAI. So, what is MAI? MAI is the tree level mass of the ith particle. Okay. And this is a distinction, okay, between the Polyakov amplitude and the S matrix element. Now, how do you know that Polyakov amplitude computes this, right. Why is it that it takes a limit qi square going to minus the tree level mass square rather than the fully normalized mass square? And the easy way to see this is that this limit, the fact that ki square plus mai square equal to 0, this essentially translates to Vi having conformal at 0. Having conformal at 0, okay, is a statement that you have at tree level, right, on the sphere. You describe conformal field theory on the sphere, okay, and based on that analysis of the conformal field theory, you determine what is the on-shell condition, okay, namely Vi's have to be conformal invariant, okay, and that translates to this on-shell condition over here. Okay. And this condition you don't relax when you go to hard genus. Okay, you keep working with conformal invariant vortex operator, and this is necessary if you want to use a conformal invariant formalism, right. If you try to relax this condition, then you run into all kinds of difficulties, some of which you will see as we go along. So this is the reason you know that the Polyakov amplitude, okay, computes not truly the S matrix element, okay, where the limit that has to be taken is when the k square goes to the physical mass square, okay, or minus the physical mass square. Okay. Polyakov amplitude computes the limit where k square goes to the tree level mass square or minus the tree level mass square.
Sorry, just to make sure one thing. Yes. So when you compute Gn, does it contain physical mass or does it contain tree level mass?
Well, you compute Gn by using the correlation function, right? Yes. So Gn doesn't know about any physical mass or tree level mass. Gn is Gn, that endpoint Green's function, right? That you compute in the theory.
But I require to put some propagators, right? In order to compute, say, in loop, I will have propagators in general.
You always use tree level mass. If you, as long as you are drawing all Feynman diagrams, yeah, right? You only use tree level mass in the propagator, right? The sum over diagrams renormalize that tree level mass into physical mass, right? But you never have to, when you are doing perturbation theory, right? In the propagator, you can always put the tree level mass, the BR mass, right? And then at the end of that's the mass that appears in Lagrangian, right? And the point, okay, there one distinction between the quantum field theory and string theory is that there, of course, the BR mass is infinite, right? So it's not in a normal quantum field theory you have to renormalize, so the BR mass is infinite. In string theory, because you have no ultraviolet divergence, right? You can equally well talk about BR mass and renormalized mass, all are finite, okay, but they are not necessarily equal. So if you are doing, if you are trying to reproduce the string amplitudes using Feynman diagrams, you will always use tree level BR mass, right, to compute. And eventually, if you had a field theory, okay, it will, the full 2-point function that you calculate, off-shell 2-point function, will have poles at a shifted mass, right? That will be the physical mass of the theory. Yes.
Can you comment a bit on this Gn on the case of string theory?
Yes.
You mean off-shell?
No, not off-shell, because you are in string theory, which only tells us how to compute this,
yes,
right? So what I am saying here is that if we had an underlying string field theory, right, then Polyakov amplitude will compute something like this.
So okay, so implicit is that Gn what would come from a string field theory?
That's right, yeah. That Gn would come from if we had a string field theory, right? But otherwise Polyakov amplitude only computes n, right? What I am trying to argue here is that if you had an underlying string field theory, Polyakov amplitude will not compute the S matrix element as this one. Okay. So you see that An and Sn are not equal. Well, 2-point function on the sphere, first of all, is not even well defined, right? To compute the 2-point function on the torus, right, you have to compute, see, if you want to compute, use this formula, right, you need 2-point function off shell, right, but Polyakov amplitude only tells you how to compute the on shell 2-point function, right. You can compute a 2-point function, but only when k square is set equal to minus m I square. That will not be of much help, right, in identifying the shifted pole. Okay, so this Polyakov conformally invariant Polyakov amplitudes, okay, will not be able to give you the result that you want. Okay, so you see that An is not equal to Sn in general. Yes. Why is that? No z function. Oh, because in the Polyakov amplitude, you don't do any function normalization explicitly, right? You just compute the amplitude. Yeah. So in Polyakov amplitude, if you look at the details of the computation, right, what you do is that you basically truncate the external propagators because you don't have divergent answers, right, in Polyakov amplitude. But there is no explicit computation of the z, the wave function normalization, and factoring it out. So the Polyakov amplitude doesn't know about the z factor.
But you are saying that this z coming from green function, right? This z is offset one, right?
Yeah. So this z is 2-point function. You can compute this z from 2-point function. In a quantum field theory, you would compute this z from the 2-point function, and then you have to subtract it out from the, you have to divide the Green's function by this explicitly.
So I mean, how, let's see. But if we okay, quantum field theory side, if we compute a 2-point function, we know that z factor and mass renormalization, right?
Yes.
And you say that that doesn't appear in the string field theory or something.
No, in string, I'm not only talking about string field theory here. If you did have a string field theory,
yeah,
then you could compute the z from the 2-point function. Right?
Okay.
In Polyakov amplitude, right, what it does is that it basically, so this subtraction, okay, these factors, these basically what it does is that it removes some external cylinders. Okay, so essentially what Polyakov amplitude does is that you take on shell states, you make them propagate for infinite time, okay,
yeah,
and then you compute the amplitude.
Okay, yeah.
So Polyakov amplitude basically removes these cylinders. Okay, it doesn't explicitly take into account these infinite cylinders over which you have to integrate, okay, because you start from asymptotic states and propagate, right? Okay. And removing these infinite cylinders essentially is this operation.
Yeah, that's okay. Yeah.
Okay, but there is no z here. Those infinite cylinders, right? You don't include any loop effects here.
Oh.
Okay, it's just the 3-level cylinders that we remove in the Polyakov amplitude.
Okay, so you are saying that this, suppose this green function contain z factor.
Yes.
Even though, in spite of that case, just without inserting z, then you can get this Polyakov amplitude. Is that right?
Yes. So the Polyakov amplitude, there is no z or anything. There is no Green's function, underlying Green's function, right? I'm just saying, if you just directly computed the Polyakov amplitude, okay, what it would compute, okay, is the analog of this.
This one.
No z factor is removed.
Okay, I see.
Okay, in the Polyakov amplitude, because all the Polyakov amplitude does is that it removes this infinite propagation from infinity to the interaction point, right, by a cylinder, and this factor basically contributes 1 over k square plus m square. Okay, those you don't take into account explicitly in Polyakov amplitude, right? Otherwise, of course, the amplitude will be infinite, right, because of this infinite propagation. Okay. Other than that, Polyakov amplitude keeps everything of the Green's function. Okay, so An is not equal to Sn in general, unless we have two conditions satisfied. First is that the z factor has to be 1, and second, m AIP is equal to m AI. Okay, the renormalized physical mass should be equal to the tree level mass. Okay, under these conditions, of course, An and Sn are the same. Okay, as you can see. Yes. See, in string theory, the point is there is no ultraviolet divergence, right? So, in normal way of doing it, the Bayer parameters are unphysical, right? In some sense, they are taken to infinity, and you only talk about the renormalized parameters. But here, the Bayer parameters are physical. Those are the ones that string theory gives you. Renormalization is perfectly finite. There is no ultraviolet divergence, and you are basically relating the Bayer parameter to the physical parameters, right? So here, there is no scheme dependence. Right? There is no ultraviolet divergence, so you are not subtracting of anything. Right? You keep the full loop corrections. It's like quantum mechanics, right? And everything is finite. Given the parameters of the Hamiltonian, you can compute everything. Right? And that's what you have here. Yeah, that this condition, okay, that this limit is equal recurring that the vertex operators are conformal at 0. Okay, because the vertex operator conformal to the vertex operator contain basically is proportional to ki square plus mi square. That's the way you define m for a given state. Right? And this being equal to 0 is equivalent to having conformal invariant vertex operator, namely that they have dimension 0. Well, yeah, if we have a way, but we will see that there are problems with that, right? Okay, so these two, okay, when is this true? Okay. This is true, of course, at tree level. Okay. So at tree level, indeed, Polyakov amplitude computes S matrix elements. And at tree level, we know that Z is 1, and there is no difference between the renormalized the physical mass and the Bayer mass. Okay, that's how we call this parameter mass in the first place. This condition is true also a little more generally. This is true for massless gauge particles. And also for BPS states. BPS states are states whose masses are protected by supersymmetry. So there is no mass renormalization. Okay, so for BPS states, this would be true. Okay, but even for BPS states and massless gauge particles, this in general is not true once you go beyond tree. Now it turns out that the effect of Z, even remaining within on-cell formalism, the effect of Z, this one, this factor, is not too hard to take into account. Okay, that if we had an on-cell S matrix element, you could take into account the effect of Z remaining within the on-cell formalism. However, this effect, the fact that the MAI is different from MAI physical, that's much harder to take into account. So the upshot is that if masses are not renormalized, okay, but only wave function renormalization is there, then from Polyakov amplitude, okay, there is a systematic procedure that you can follow to arrive at the S matrix element. Okay, you have to do a little more work. An is not directly equal to Sn, okay, but with some amount of work, you can go from An to Sn. Okay. But if these are not equal, okay, unless this condition is satisfied, there is no simple way to go from An to Sn. Well, I will not tell you. I mean, basically, what you have to do is that you basically have given an S matrix, it has to satisfy certain factorization property, right? On a pole, one S matrix should factorize into products of lower point S matrices, right? And basically, the point is, if you don't choose the Z's correctly, that will not be satisfied, right? That will be satisfied only up to some normalization. So by looking at that property, right, you can figure out what the Z's should be. right? That suppose you take the Polyakov amplitude A n, right? It will not satisfy that property directly because you have not fixed the Z's correctly. But you have to, you see that how much is violated, and that will fix your Z. So, n used to compute Sn only if MAIP is equal to MAI, okay, but not otherwise. Now, of course, you must be wondering that this is an old problem in string theory, so how come nobody talks about it? Okay, now the point is that it's not that nobody talks about it. People did worry about this problem a lot near the initial days of string theory, okay, but none of the approaches really went very far. Okay, up to at one loop there are various prescriptions of how to deal with this, but beyond one loop people didn't really know what to do. Okay, there is no systematic algorithm to resolve this problem. But then people also found a common excuse, okay, which they used basically to sideline this problem. Okay, so let me tell you what the common excuse is, okay. And it's going to be useful because even though, as we will see that even though this excuse is not valid, okay, we will make use of it later in the course of lectures. So what is the excuse that people use? So the excuse that is used is that poles in the S matrix of massless or BPS states contain information about physical masses of massive states, masses of general states. So let us imagine that we have an S matrix, okay, of some set of external states. Let us say K1 to Kn and L1 to Ln, L1 to Lm. Okay, these are the external momenta. These states are all massless or BPS. Okay, so there is a problem in defining this S matrix. Now let us suppose that K is the total momentum flowing in this direction. Okay, so K essentially is sum over Ki or equivalently minus sum over Li. So what you can do is that you can examine the pole of S matrix element as a function of K square, and those poles essentially come from intermediate states propagating in this channel, right, by the standard factors and property of S matrix elements, okay, which of course goes beyond tree level, right. It is a generally valid statement. So you can look at the poles in the S matrix element in this channel, and the locations of those poles are basically the physical masses of various massive particles. Okay, so essentially the poles will come from factorized S matrix like this, okay, where this momentum that is flowing here is K, okay, and if the mass of the state, if the physical mass of the state is m AIP along this channel, then this will give a pole of the form 1 over k squared plus m AIP square. Okay. So in principle, then you could examine, you could just start with the S matrix of massless and BPS states, okay, and then examine all its poles in various channels, and looking at those poles, where the poles occur, you can figure out where the physical masses are, okay, and you can also generalize this procedure to compute the S matrices of these intermediate states, okay, and for the residues at these poles can be used to compute the S matrix involving the states which are propagating here. Yes. In a Feynman diagram, yes, indeed, we can get a line like this, right? But this property is valid with respect to Feynman diagram, right? This is just the standard analyticity property of the S matrix, that the poles in the S matrix come from essentially intermediate tonsile states, right? So you are basically using this. If you had an underlying quantum field theory, then of course the Feynman diagrams will have intermediate states propagating here. Right? These are one particle reducible Feynman diagrams. Exactly. One particle irreducible ones in this channel, the ones which are one particle irreducible in this channel will not give poles. Right? So by looking at the locations of the poles, you identify the physical particles, physical masses. No. LZ for this GN in LZ formalism is the full Green's function, right? Not one particle irreducible diagrams. Okay, so what is the problem with this? Okay, why don't we use this formalism? Okay. Problem, of course, it's cumbersome. Okay, we are not going to use this kind of technique, okay, to compute renormalized masses, right? It's like, I mean, if somebody tells you in standard model to calculate the Higgs mass, right, you have to calculate the 4 photon scattering and then look at the pole in the channel where the Higgs might be produced. Okay, it's going to be a much more complicated calculation than directly computing the Higgs mass, right? So this is, but okay, this is a question of practice. Okay, in principle, okay, if this was always allowed, if this was always valid, we could say that okay, we can live with it. Okay, we only deal with massless external particles, massless and BPS external particles, and don't worry about massive external leg. You get all factoring using this kind of approach. But the main problem is that it does not always work. Yeah, this is a problem of principle. You can see under what condition it will fail to work. Let's imagine that there is a massive particle which carries a quantum number that none of the massless or BPS particles carry. Okay. In that case, conservation law will prevent production of the massive particle in the intermediate channel, right, as one particle intermediate channel, just by looking at the S matrix of massive of massless and BPS states. So this procedure will fail for those particles. And there is in fact a very standard example, okay, which I will describe here. And this example deals with S authority to heterotic string theory in 10 dimension. Okay, if you don't know what it is, you don't really need to worry about it. Okay, except one particular fact. Okay. And that fact is that it has massive states in spinor representation of S authority. But massless states are in adjoint Okay, there are no BPA states in 10-dimensional heterotic string theory. So you see from here that it's impossible to produce any one of the states, okay, which is in the spinor representation of SO32 by colliding singlet and adjoint representations, right, as one particle intermediate state. Okay, it's just inconsistent with the SO32 group theory. So if you are trying to compute the mass of this particular state in heterotic string theory, okay, which is in the spinor representation of SO32, you cannot get it from this kind of approach, okay, because such a state will never appear as a single particle intermediate state in the scattering. So you really have to deal with this problem head on. Yes.
So another way to do it, which is more complicated, would be to look at a branch cut that might appear.
Yeah,
Is that
but that's,
complicated to do?
well, it's in general much more complicated to look at branch cuts, and for branch cuts it's not even completely clear that you can fully separate out the various contributions, right? Or you can calculate the S matrix element, for example, of these particles using the branch cut. Usually look at the, yeah, I agree. In principle it is possible, but I think in practice it's much more difficult. Okay? And particularly if you are looking at the higher states in that channel, right, not the lowest order branch cut, but the higher order ones, then it becomes extremely cumbersome, right? Particularly if because there are massless states, right? Once the branch cut starts, right, it will keep producing those massless states, and you basically have a continuum, right? So the next order branch cuts are very hard to detect from these amplitudes. Yes.
You will always have all these poles in the
Yeah,
at case
I think
equal to
it's a
minus
more
m square.
general statement on the analyticity property of the S matrix element, that if you start with a n-count S matrix element, right, then the poles of that S matrix element in any particular channel will come from the intermediate single particle states. Right? This is a more general statement. Yeah. Okay. In a sense, you can think of this as a two-point function, that where on one side you have all these things, right, that this is one particular object and there is another particular object, right? It's a two-point function of composite objects. Okay. So the solution, at least the most straightforward solution, yes. Yeah. Well, actually, first of all, it's a question of principle, right? Whether the string, if string theory is to be a consistent theory, right, then any question you can ask within perturbative string theory, you should be able to answer, right? So you cannot simply say that there are some quantities in string theory that there's no to compute, right? More specifically, okay, this is, if I have in the sometime in the last talk I can discuss this. My interest in this came because I really wanted to study these quantum corrections to the SO32 spinor masses, right, for some quite a different purpose. Right? And the point is that one loop you can do it because beyond one loop there is a systematic procedure. Yes, so you cannot even start asking that question unless you develop a systematic procedure. Okay. Yes. Yeah, that if you take SO32 heterotic string in 10 dimension, we know that it has massive states in the spinor representation of SO32. Right? And all the massless states are in the singlet and adjoint representation.
Okay.
Right? So if you scatter massless states, right, and try to get this SO32 spinor, look for a pole corresponding to the SO32 spinor state, you will never find it, because you think of here that suppose all these states are in the singlet and adjoint representation, right?
Okay.
then S-O32 group theory prevents the production of a spinor state.
But won't that be a problem with unitarity? I mean, all channels must be present in the intermediate states in various ways.
That is true, but if the point, if some particles
Yes.
are prevented from, not all states are appear as intermediate states, right? Because the charge conservation may prevent some states from appearing in the intermediate state as intermediate state, and that's what is happening here. That the SO32 charge conservation prevents the appearance of the single particle intermediate state, right, in this scattering. Right? So you should produce all intermediate states consistent with charge conservation.
So I think particles and antiparticles, or particles with the opposite charge, will be produced.
Yeah, so the pair will be produced.
Yes.
Right? That's what Sandeep was saying. So you can try to get branch cuts, right? But looking for branch cuts in a scattering amplitude and trying to extract the physical masses in S matrix is a very hard problem.
Thanks.
Okay? If you produce poles, then at least in principle there is a well-defined prescription. Okay. So the solution is to go off shell. Okay, you generalize Polyakov prescription to compute off shell amplitudes. The problem, okay, now of course, the reason that people don't talk about off shell string theory, okay, is because it has various problems, right? Otherwise, people could formulate string theory off shell from the beginning. And the problem that we have is that off shell amplitudes depend on spurious additional data. Additional data on the world sheet.
Follow on from that.
Yes.
Suppose I scatter this massless state as you said. In the intermediate, I may not get this spinor, but I'll get many other massive states, right?
Yes.
But now suppose I know the renormalized mass for them, and then I try to scatter them.
But they will never produce this spinor, right? Because all of those massive states will be all in different conjugacy classes of SO32, right? You think of SO2, right? Suppose you only had integer spin particles. You scattered them and you produce other integer spin particles, right? Their masses you can calculate this way. But by scattering those, you will never produce half integer spin particles, right? So it's the same problem here. Okay. So what do you mean by this? Okay, that they depend on spurious additional data. Okay, it's best illustrated by looking at an example. Okay, what exactly you mean by this? So example, say off shell 3 tachyon amplitude in bosonic string theory. The simplest possible thing you can think of. 3 tachyon amplitude. In bosonic string theory. So this one is given by the following correlation function, and we look at 3 level. Okay, so even simpler. At G equal to 0. What is Vi? Vi is e to the I ki dot xi, ki dot x. Okay, these are the external moment of the tachyons. Okay. And the on shell condition, which you want to avoid. Okay, but let me write the on shell condition anyway. On shell condition is ki square by 2 minus 2 equal to 0. So, this 4 or minus 4 is basically the tachyon mass square. I think not, it's plus 2, no, minus 2. Yeah, this is fine. Yes.
When you go offshell, in principle, the leisure degree of freedom will appear.
Yeah, but we are not going to, the point is we are not going to go off shell in the sense that we are not going to make the world sheet theory. So, what we are going, by going off shell here, you mean only the vortex operators we take off shell, right? Not that the world sheet, you break conformal invariance on the world sheet completely. Okay, so this, for dealing with this, you don't have to really introduce the Liouville degrees of freedom. Right? That is a pragmatic way of doing this. Right? That's what you are going to describe. Okay, so let's measure this degree of off-shellness by this quantity delta I, which is ki square over minus 2. Okay. And this, in fact, you can show is the total conformal weight of Vi. Conformal weight. So that you can, it's clear from here that the on-shell condition is equivalent to demanding that the each vortex operator is conformal invariant, right? Because when the on-shell condition is satisfied, delta I is 0 and everything is conformal invariant. So that's when we expect the Polyakov prescription to be free from any ambiguity. Okay. So in any case, okay, we can compute this. Okay, it's just a simple 3-point function on the sphere or on the plane, and what we find is the following answer, given by mod z1 minus z2 to the power delta 3 minus delta 1 minus delta 2 mod z2 minus z3 . Okay, so this is the off shell 3 tachyon amplitude in the theory. Now you see that there is a problem because what are these rates? Right? And when you do 3 tachyon amplitude, the final result should only depend on the external momentum, right? There should be no dependence on these z's. What are these z's after all? Now, when we write this as the 3 tachyon amplitude, right? So let's go back to the Polyakov amplitude as an on-shell amplitude. Suppose you are dealing with on-shell 3 tachyon amplitude. Okay. Then we see first of all, there is no dependence on z in that case anymore, right? Because all of these deltas are 0. Okay, it's just 1. Okay. But there is also a reason why there is no z dependence that appears, okay? Because on shell this 3 tachyon amplitude, or in fact any general amplitude, okay, on a genus 0 surface is supposed to be invariant under SL2C, invariance under SL2C transformation, okay, under which each Zi basically goes to A Zi plus B over C Zi plus D, AD minus BC equal to 1. Now, if this was really an invariance of the amplitude, then using this transformation you can choose, we can make these Zi's into 3 arbitrary points, okay, and the result should be independent of where you put those 3 arbitrary points, right? And that is the reason why when you actually describe the Polyakov amplitude for 3 tachyon on shell, we don't specify what the Z's are, okay, because the result is supposed to be independent of the Zi's because of this underlying SL2C invariance. But this is broken. This is broken, and because this symmetry is broken off shell, the result starts depending on spurious data like Z's, okay, which have no business being there in a genuine string amplitude. So, this looks problematic. Okay, and in fact, this is the reason why people do not talk about optional amplitudes in string theory. Okay, that you can define optional amplitudes, but that will start depending on additional data, okay, which we should not have in a properly defined string theory.
Sorry, Ashok, just to, this is the amplitude with C1, Z2 and Z3 as some fixed point.
Yes.
But then of course we would have to integrate over the...
No, in 3-point function you never integrate, right? This general 0 3-point function. I mean, the reason that we don't integrate is because of this SL2C invariance, right? We say that we can take any set of C's to any other set of C's, right? For 3 of them, the 4th one will have to be integrated, but for the 3, you can fix them anywhere.
Okay, so you use the SL2C
to fix it,
to fix them.
and then you find that the SL2C is actually broken because the result does depend on the sets. And this is the reason it looks problematic, because it depends on the extra data which shouldn't come in here. Now, even though this looks like bad news, I mean, we can go back to the story of gauge theory in normal quantum field theory and compare with the situation there. So, in gauge theory, okay, so recall some facts in gauge theory. There, if we take an off-shell Green's function of charge fields, these are gauge dependent. Okay, if you calculate, for example, say Green's function, right? 2 electron, 2 positron Green's function in normal QED, the result for that result of that computation will differ in the Feynman gauge and Landau gauge and axial gauge. Okay, so the off-shell Green's functions are dependent on gauge fixing parameters. But you know, of course, that the gauge dependence cannot be physical, right? The gauge that we fix is not is the analog of the spurious data that we have here. Okay. Gauge that we fix is something that we choose, right? It's not inherent from the theory. Okay. So it's not surprising that when we try to deal with off-shell Green's functions, right, we will have some problem, okay, of this kind, okay, that it will start depending on additional spurious data. Okay. Nevertheless, we do talk about off-shell Green's functions in quantum field theory, right, in gauge theory. The reason that we do it is because even though the off-shell Green's functions themselves are gauge dependent, we can extract from them quantities which are gauge invariant. And these quantities are precisely quantities like renormalized mass and S matrix element. So, nevertheless, renormalized mass and S matrix elements are gauge invariant. But to compute this, we have to go to this intermediate step of dealing with gauge dependent quantities. Right? For example, if you want to calculate the renormalized mass of the electron, you have to deal with 2 electron Green's function, right, and then look for its pole. And that object, the intermediate object that you deal with, 2 electron Green's function, is a gauge dependent quantity. So you could ask whether the story in string theory can be something similar. Okay, I guess I have completed my 1 hour, but I can go on. Okay. Okay, so this is the central question that we will try to address. So, the strategy that we will be following will be in 2 steps. The first step is to characterize the spurious data So, these will be the analogs of the Z1, Z2, Z3 that I described, right. I looked at the 3-point function of the tachyon and we saw that it depends on the spurious data, right. There is Z1, Z2, Z3, but what is the general characterization of the spurious data for a general n-point function on the genus Riemann surface? Okay, so that's the first thing we have to deal with, because before we see whether things are independent of this, okay, at least we should characterize what is it that we are trying to prove that things are independent of. Okay, so that's the first step. So, characterize the spurious data systematically, and then show that physical quantities like renormalized mass and S matrix element are independent of the spurious data. So, let me do the first step, okay, and that will be the last topic of today's lecture, that is to characterize the spurious data. Okay. So, take a Riemann surface sigma Gn of genus G and n punctures. Okay, which basically means that we are going to use this to compute an n-point amplitude. So, we will denote by Z some reference coordinate system, some holomorphic reference coordinate system, of course, reference coordinate system on sigma G. Okay, Riemann, basically Riemann surface is a two-dimensional surface which can be parametered by one complex coordinate system parameter. Okay. Of course, it may have to be done in patches. Okay, so basically this quantity Z will stand for the system of coordinates on various patches. Okay, but there is some fixed coordinate system that we choose. Okay. Now, if our experience from the 3-point tachyon computation is to be believed, okay, it would suggest that the final correlation functions will start depending on this reference coordinate system. Right? If you use a reference coordinate system and write the correlation function, the result will depend on that coordinate system. Right? But we will try to avoid that situation. Okay? And we will see how exactly we avoid that situation. So, to do that, we will now introduce another set of coordinates which we call local coordinates. So, this is the first set of coordinates that we have. The second set of coordinates is that around every puncture Wi, around every puncture, choose a local coordinate Wi such that Wi equal to 0 corresponds to Z equal to Zi. This is a point where the ith punctured, point where the ith vertex operator is, or where the ith puncture is. So, in general, then Z and W will be related by some functional relationship. And for a fixed Z, as you change W, this function will change. Right? Different choice of local coordinates will be related to Z by different functions. But we will demand that Fi of 0 is Zi. Okay, because this is the statement, the Wi equal to 0 should map into Z equal to Zi, right? So, even though as you change this local coordinate system, you should make sure that the origin of the local coordinate system always map to the point Z equal to Zi, where the puncture, where the vertex operator will be inserted, that ith vertex operator. Pardon? Well, this is the way we are choosing the local coordinates. Right? We want to make sure that the local coordinates are chosen so that the vertex operator is inserted at the origin of this local coordinate system, right, for the ith function. Right? That's how we are defining our local coordinates. Okay, you can relax this, but it doesn't get you any advantage. Okay, so you can restrict to this condition. We also introduce another notation, Fi circle Vi of W. What is this? This by definition is the conformal transformation of Vi W by the map Fi. So, let me give an example of what we mean by a conformal transformation. Okay. Example is, suppose Vi of W is a primary of dimension HH. Okay, left dimension and right dimension are equal to H. Okay. On shell, of course, H would have been 0. Okay, but now we are dealing with off-shell vertex operators, right? So that's why they can have non-trivial conformal weight. Then Fi dot Vi of W will be F prime of W, Fi prime of W to the power 2h Vi of F of W. Okay, this is the way a primary field transforms. If Vi had been not a primary, okay, but a conformal secondary, there will be more complicated transformation. Okay, but it can be worked out. It's just a simple conformal field theory. Two-dimensional conformal field theory tells us that given any vertex operator of certain conformal weight and certain conformal properties, it can be a general secondary, how to apply a conformal transformation on this vertex operator to generate the transformed object. Okay, for primary it's simple. For secondary there are additional terms which involves various higher derivatives of F. Okay, but this is a well-defined object. And we are going to define our off-shell amplitude with the help of these objects. Okay. So let me now write down the off-shell amplitude.
Sorry, Ashok, yes. So far the only condition on omega I is that it vanishes at Zi, right?
Yes, and the relationship between Z and omega, Z and W, is analytic near W equal to 0. Right? So the Taylor series expansion of F should be all perfectly regular.
No poles or any other.
Exactly, that's right. Okay, so Fi of 0 is 0. Sorry, Fi of 0 is equal to Zi, right? And then there is a well-defined Taylor series expansion. Okay? And that is necessary in order to be able to define this. Okay, because to define this, okay, you have to make sure that you can calculate various derivatives of Fi. Right? And that requires the Fi to be analytic. Yes, it contains also the marked points, it contains everything on a Riemann surface.
In complement of these points.
No, you define, as I said, Z coordinate is defined in coordinate patches, right? So in each coordinate patch, it's all finite, right? So Z is never infinite. So relationship between Z and W is always finite.
To contain all these points, marked points, but is it always possible on a general Riemann surface?
If you are allowing patches, right, you can always do this, right?
No, but Z is a single coordinate.
No, that's what I said. It's not single coordinate, it's a reference coordinate system, but it can be a collection of coordinates in different patches, right? But you fix the patches and you fix these coordinates once and for all, right? That's all we are saying. Right? It need not be a single coordinate that covers the full Taylor series. That's of course not possible. Okay, so define off-shell amplitude. N, which will be integral of sum over G 0 to infinity integral mgn these are the usual ghost insertions. So this you see is very similar to what we had for on-shell amplitudes. Only difference is that for on-shell amplitudes we have put Vi of Zi here. Okay, the Polyakov prescription involved a Vi of Zi that we have replaced by this object over here. But this is equal to, let's see what happens if V was on-shell. if this was on shell, then H will be 0, right? On shell vertex operators are conformal invariant, right? For on shell vertex operators, H would be 0, so this factor is absent, okay? And you will get Vi of Fi of 0, okay, because you are evaluating it equal to 0, as you can see, argument there is 0. So Vi of Fi is nothing but Vi of Zi. Fi of 0 is Zi. So this would be the regular Polyakov amplitude on shell. Okay, but we are defining the off shell generalization. Instead of writing here Vi of Zi, we put Fi dot Vi of Zi, so that there is an extra conformal factor that comes in this transformation. Is this clear? Now this looks like a complicated way of doing this. Why didn't we just put Vi of Zi here? Right? Why this? And the reason that we have done this is because with this definition one can show that N is independent of the choice of Z coordinate system and depends only on the choice of local coordinates Wi. Okay. And I will just illustrate this by again the tachyon 3-point function example. Okay, because this looks a little abstract, so I think once we have an example it will become clear. So example, tachyon 3-point function at g equal to 0. So what is the difference between the previous case? Now we are defining A3 as product I equal to 1 to 3 Vi dot Fi dot Vi of 0. So this is given by Fi prime of 0. You see mod Fi prime of 0 to the power 2, right? I am using this formula over here. But 2hi is nothing but delta I, total conformal weight of this. Okay, delta I, remember, delta I was ki square over 2 minus 2. Okay, this is the conformal weight. Conformal weight of Vi. Times V1 of Z1, V2 of Z2. So this is product I equal to 1 to 3 Fi prime of 0 to the power delta I Z1 minus Z2. Okay, so just to summarize, this is the factor that we had earlier. Okay, this is what we found depends on the choice of the Z coordinate system. Right? That was a problem. Now we just have this additional factor, mod Fi prime 0 to the power delta I. And what we are going to show is that this quantity is invariant under the SL2C transformation on the Z coordinate system. And that's what I mean by saying that it's independent of the choice of reference coordinates. Right? It of course does depend on the choice of the W coordinate system. Okay? If you change the W coordinate system, then the FIs change. Right? Nothing happens to this, but the FIs change. That obviously will change the correlation function. Okay? But this is not dependent on the choice of Z coordinate system. Okay? That's what we are going to describe. No, SL2C will not make this Z independent, right? This factor still depends on the Z's, right? You have to show that this cancels it, that dependence that comes here. Well, let's say that they will full become invariant under the SL2C transformation, right? The three parameters of SL2C, the ABC, right? It will be independent of that transformation, right? That's what I will show.
Without the factor f in front, the rest of it has the proper structure of a 3-point function of 3 primary operators.
Yes, this one is
Say this,
an overall multiplicative factor. This comes because you have to first Cosmology transform this VIs. Well, if you take each primary operator and multiply it by something, right? It's also a primary operator. That's what you have done here. So for primary operator, the only thing is that each primary operator gets multiplied by some additional factor, right? Right? So this is still perfectly good 3-point function, right? This factor has come because each primary operator has been renormalized by this additional factor of a5 prime 0 to the power delta, right? And that comes from this transformation. Right? So the point is that we are doing, so we have to use the correlation functions that we get in conformal field theory, right? But those correlation functions depends not only on the theory that that you are using, but also what vertex operators you are using, right? And what we are saying is that instead of using Zi, which would have just given this, we are using a different combination of vertex operators, which is the transform of Vi by this conformal transform Fi. Right? And because of this, we are getting this additional factors. Right? So this is also perfectly consistent with all the conformal invariances. Right? The difference is that we are using just different operators. Right? Not just Vi of Zi, but Vi of Zi multiplied by something. Right? Now the reason that written it this way is because this way of writing it is also valid when Vi is not primary. Right? If Vi is not primary, then we will not have just this factor. There will be more complicated transformation. But nevertheless, this statement is valid for all operators. Right? I am going to demonstrate this only for this primary operator. But the fact that the correlation functions are independent of the choice of reference coordinate system is valid in general. Okay, that's how you have divided it into this in this fashion. Okay. But let's just see how this becomes SL2C invariant. So under SL2C, Zi A Zi plus B over C Zi plus D. Okay, so let's call this H of Zi. Okay, where H is this function. Okay, H of Z is Az plus B over Cz plus D. So H of Z is Az plus B over Cz plus D. So how does Fi change? So Fi of W, if you make a transformation like this, Fi of W will go over to H of Fi of W. Right? Because you are keeping the W coordinate fixed, you are just changing the Z coordinate. So Fi prime of 0, prime is the derivative with respect to the argument. This will go to H prime of Fi of 0 times Fi prime of 0. Okay. So which is H prime of Zi times Fi prime of 0. And H prime of Zi from here, this is I think C Zi plus D to the power minus 2 times Fi prime of 0. So you see that now if you make an SL2C transformation on this factor will change, right? Under Zi goes to that Azi plus B over Czi plus D. This is not invariant, but I'll leave it as an exercise to check that this transformation of this that we see from here precisely cancels the factor that we get from here. Okay, and hence the choice of reference coordinate system Z does not affect the correlation function. If you make a change of the reference coordinate system Z, in this case by SL2C transformation, this would have been changed, would have depended on the, wouldn't have been invariant, but this combination or this combination more generally is independent of the choice of the Z coordinate system. Okay, you make an SL2C transformation, you get the same result. Exercise, check that A3 is SL2C invariant. So, what we see here is that the choice of local coordinates is the spurious data.
Only for the 3-point function.
But
This is showed only for the 3-point
yes,
function.
but what this is the statement is valid in general. Right? I have not shown this, but this is valid for arbitrary genus Riemann surface. That once you divide it in this way, the local coordinates and the reference coordinate, and once you define the genus G amplitude by transforming by these FIs, right, that relates the reference coordinate to the local coordinates, then this is valid in general, that the reference coordinate system dependence drops out completely. All the dependence, pardon? For the
Sphere.
yes, yes. No, it's not for sphere. It's in general. The result is valid in general. Right? I have only demonstrated this for sphere.
So then, okay. So you're saying that that can be also shown.
Yeah, it can be shown that for a general Riemann surface, right, this is true. That once we have defined our off-shell Green's function by this particular procedure, then the only dependence that comes is to the choice of local coordinates.
Okay, bosonic state like tachyon we considered here. But
Yeah,
supposing
for
that
any
one-
general scale.
for
It
a
can be primary, secondary, anything, right? This VIs can be anything. So what I have done here is that I have illustrated this by this example, right? But the statement is true in general on any Riemann surface. The only dependence is through the local coordinate system.
I mean, one way to say it is that the Fs have been chosen so that starting from any general Z coordinate system, you can always convert the calculation into the local coordinates batch-wise.
Well, not really, because the correlation function of course has to be calculated globally, right?
Yeah.
But the dependence on the, to the point is that so why is this distinction important, right? The distinction is important because you are not breaking control invariance in the theory. Right? The breaking of the control invariance is only through choice of the vertex operators. So what one would expect is that the dependence that the spurious data on which it will depend, right, will depend on the data near the vertex operators, but not how you have chosen the coordinate system on the rest of the Riemann surface. And this distinction between local and global coordinate system makes this manifest. Right? It makes it manifest that the dependence, the spurious data, is only on how you have chosen the coordinate system near the vertex operators. Right? How you have chosen to insert the vertex operators, which coordinate system you are inserting the vertex operator. Right? Yes.
Suppose you had retained the Liouville mode,
Yes.
vertex operators. Then also this kind of will take place. So when you make a transformation on the vertex operators, the Liouville mode will
Exactly. Yeah. Yeah.
Finally sort of transform so that it remains.
I completely agree, right? So the point is, we are not going to put in the Liouville mode at all, okay? But we are going to live with this fact that the off-shell correlation functions that we are defining depends on some spurious data, which shouldn't be there in the first place, right? So we live with this fact, but nevertheless, the goal will be to show that physical mass S matrix elements are independent of this data, are independent of the choice of local coordinates. Okay. So the point is that at this stage, it looks like an ad hoc prescription. Right? As you said, that if you really try to start with the worldsheet path integral over metric, etc., then you would imagine that there may be Liouville mode stuck at the vertex operators, right? But you are not going to do that, right? We give this ad hoc prescription that we simply forget about Liouville mode and insert the vertex operators in some local coordinates, W coordinate system. Then we go ahead, okay, that's our definition of off-shell vertex operator. Now things start depending on how you have chosen those local coordinates. But we'll proceed with that, okay, keeping in mind this gauge theory example that at the intermediate stage in gauge theories also you have to deal with off-shell Green's functions which are not gauge invariant. But at the end, if we can show that the physical quantities are independent of the choice of gauge, that is enough. Right? So similarly here, if we can show that the physical masses in S matrix elements are independent of the choice of local coordinates, then you have achieved our goal. Right? Even though at the intermediate stage you had just used this ad hoc definition of off-shell Green's function, which depends on the spurious data. So that will be the goal of the rest of the lectures. Thank you.
Okay, so there have been quite a few questions or something. If there's something very pressing, we can have it. Otherwise, there's the discussion session.
So this tachyon, like I would have like a graviton, means where not only the vertex operator, but also I have other conditions which tells me that this operator is graviton.
So all of those conditions are relaxed to go offset.
That should be relaxed, right?
Yes.
So it's not like zeta dot k has to be equal to 0. But
all of those will be relaxed, right? So that the vertex operator will not be primary anymore, right? But nevertheless, this is particularly different, right? When we are doing psi equal to 1 plane, this f dot b, what you have to insert in the correlation function is completely well different, right? You just have to do one further, right? If it's not primary, then f transform of b is a more complicated one, right? Nevertheless, it can be calculated, and the prescription is that you calculate it, you put it in the correlation function, right? That's your definition of the off-shell approach. That depends very much on the choice of local coordinates. Okay, it's independent of the choice of reference coordinates, but it does depend on the choice of local coordinates. But you have to show at the end that the physical S matrix elements that you compute from there do not depend on this data.
Okay, let's thank Ashok again.